Hello viewers, welcome to AJ Khan Geotechnical Forum, and today I'm going to talk about the concept of effective stress, and this is my lecture number 3 in this forum. Let us take a soil mass with no water in the void spaces. That means the degree of saturation of this soil mass is 0 and the soil is in its dry state. Now, on this soil mass, if we apply a load that causes a total stress equal to sigma, this total stress will be taken by the soil particles at their contact points. So, through the reaction of the soil particles at their contact points, this total stress will be carried. So the total stress will be carried by the individual particles or the soil skeleton itself. Now the stress applied to a soil mass carried by its soil particles is called the effective stress. That is denoted by sigma prime, and the total stress is denoted by sigma. So this is the definition of effective stress. For your better feeling, I would say the stress that is carried by the skeleton of a soil mass or the solid particles or the individual particles, that bit is called the effective stress and is denoted by sigma prime. So for this case, when there is no water inside the void spaces, that is, there is 0 degree of saturation, the effective stress will be equal to the total stress. That is, all the stress will be carried by the solid particles alone. Now let us take another scenario where the soil mass is, the void spaces in the soil mass is completely filled with water. That is, the soil mass is in 100% degree of saturation state. And now if we apply a load that causes a total stress equal to sigma, now this total stress sigma in this scenario or in this case will be partly carried by the individual solid particles at the contact points, and also the part of it will be carried by the water in the void spaces. So the part of the stress that is carried by the solid particles by our previous definition is the effective stress, that is sigma prime, and the part of the stress that is carried by the water or the water in the void spaces is called the pore water pressure, okay, or the pore water stress, and is denoted by U. So we can write an expression that is effective stress is equal to total stress minus the pore pressure. Sigma prime is equal to sigma minus U. Okay. Now let us take an example for further understanding. So we have a soil mass in its dry state, that is, the degree of saturation is 0 and there is of course no water in the void spaces. And the dry unit weight of this soil mass is 16 kilonewton per meter cube. And let us consider a point 3 meter below the surface, point A, okay, 3 meter below the surface. Now we want to calculate the total stress, effective stress, and pore water stress at this point of the soil mass. So the total stress is obviously gamma times Z, that is 16 times 3 is 48 kilonewton per meter square, and there is no water inside the void spaces, so the pore water stress will be 0, and the effective stress will be total stress minus the pore water stress, and of course in this case the total stress will be totally or completely taken by the individual solid particles. So the effective stress in this case has to be equal to the total stress. Now let us take another example of a saturated soil mass, and when the soil all the voids are filled with water, the unit weight is the saturated unit weight, of course, because the soil is completely filled with water, the void spaces are completely filled with water, and the degree of saturation is 100%. And the unit weight in its saturated state is slightly higher than in its dry state and is equal to 18 kilonewton per meter cube. And for the same point, 3 meter below the surface, we'll now calculate the total stress, pore water stress, and the effective stress. So the total stress is again gamma times Z, which is 18 times 3 is 54 kilonewton per meter square. And the pore water stress, we have assumed that the unit weight of water is 10 instead of more precise 9.81. I have used 10 just for simplicity in calculation and also for easy remembering the unit weight. For all practical purposes, you can use unit weight of water as 10 kilonewton per meter cube, which is okay. So the gamma W times Z is 10 times 3, which is 30 kilonewton per meter square. And the effective stress is obviously the difference between the total and the pore water stress, and that should be equal to 24 kilonewton per meter square. Just for a comparison, go back to the previous example. In here, the unit weight was 16 kilonewton per meter cube, but we had an effective stress equal to 48 kilonewton per meter square. And in the next example, the unit weight was 18 kilonewton per meter cube, but we have a less effective stress carried by the solid particles, that is 24 kilonewton per meter square. The difference is obviously caused by the presence of pore water in the void spaces. Okay. Let us now go further, and again we are considering the same saturated soil mass of gamma sat equal to 18 kilonewton per meter cube and considering the point A 3 meter below the surface, but in here we have a different scenario. We have a water table rise or water level rise of 1 meter above the surface. And let us now calculate the total stress, pore water stress, and the effective stress at point A. So the total stress is 18 times 3, that is okay, that was previously there, and there will be an addition of stress due to this water column, and the height of the water column is 1 times the unit weight 10. So the total stress now, instead of 54, now it is 64 kilonewton per meter square because of rise of this water level. And the pore water stress now, instead of 10 times 3, there will be an increase 10 plus 1, 10 times 1, and that is 40. So the effective stress is still 24 kilonewton per meter square. Earlier also, the effective stress was 24 kilonewton per meter square. In this case, with a rise in water level, the effective stress remains the same. And this thing is to be noted. Let us go further. Now, for the same saturated soil, instead of an increase in water level of 1 meter, if there is an increase in water level of 2 meter above the surface, let us now calculate the effective stress again. The total stress is 18 times 3, and the stress due to this 2 meter water column will be additional, so that will be 2 times 10 additional, and the total stress is increased 74. The pore water stress will be 10 times 2 plus 10 times 3, 10 times 2 plus 10 times 3, 50. But the effective stress again remains the same. That means for a saturated soil mass, there is no effect of water column above the surface on the effective stress in the soil element below the surface. Okay, so we can draw an inference from this examples from example 2, 3, and 4 that for a submerged soil, effective stress at any depth below the surface is independent of the height of water column above the surface. Okay, so during flooding situation, for example, the minimum effective stress will be effective stress in the subsoil will occur when the soil is already saturated. Okay, now if the water level rises above the surface during flood, the effective stress is not going to be worse. Let us take another example. Say this is a cross section of a river, a small river, let us say, or a pond, if you like. Okay, there is water inside in this river, okay, of height 3 meter. Of course, the soil below the river bed is saturated, and the unit weight is 18 kilonewton per cubic meter. And let us consider a point A 2 meter below the river bed and calculate the total stress, pore water stress, and effective stress at point A. So the total stress is 3 times 10, that is the weight of this water column, plus 2 times 18, that is the self weight of the soil itself below the river bed. So that amounts to 66 kilonewton per meter square, right? And the pore water stress will be 3 plus 10 because the soil is saturated, so there is water in the void spaces of this soil as well. So 3 times 10 plus 2 times 10, 5 times 10 will be 50 kilonewton, and the effective stress is obviously 16 kilonewton per meter square at this point A. Okay, now let us say that the river, the cross section of the river is now full. Okay, it is running to the full capacity. The flooding has not yet occurred. So this is 6 meter depth of the river cross section. The soil is saturated here. Let us consider the same point A 2 meter below the river bed, and the total stress now will be 6 times 10, that is the weight of the water column, plus 2 times 18, the soil itself, that is 96. The pore water stress will be 6 plus 2, 8 times 10, and the effective stress is still the same, that is 16 kilonewton per meter square. Okay, earlier also the effective stress at point A was 16 kilonewton per meter square, but that time, in that instance, we had water height up to 3 meter. Now the river is running full, but still the effective stress at point A is the same. So our previous inference still holds for this example as well. That is, no matter what is the height of water column above the river bed, the effective stress at any depth below the river bed doesn't change. These things are very important to understand for all your future purpose. If you want to be a good practitioner, a good geotechnical consultant, all these concepts have to be very, very clear in your mind. Now let us see what are the sources that may change the effective stress in a soil mass. Let us take one simple example first. The change in effective stress in a soil mass may be caused due to wide area field placement. I'll show you. So so this is a soil system that is occurring naturally, okay, in the nature. The top layer is a clay layer and the underlying layer is a sand layer. The water table is here at the top, that is at the surface. So both the soil layers are fully saturated, and the saturated unit weight of clay is 18 kilonewton per cubic meter. We want to find the effective stress at a point A, which is 2 meter below the existing ground surface. So with this scenario, or in this scenario, the total stress will be 2 times 18, that is 36. That is the initial scenario. That is why we are saying sigma subscript A naught. Okay. And the pore water stress in this initial scenario is 2 times 10, which is 20. And the effective stress at point A is, of course, 36 minus 20, that is 16 kilonewton per meter square. Now, if a wide area fill is placed above this clay layer, by wide area means we mean the width of this surcharge or the fill is very, very high compared to the thickness of this clay layer. Okay. For example, if the thickness of this clay layer is say 4 meter and the width of this fill is say 40 meter, so that can be considered as a wide area fill placement. And the unit weight of this fill is the bulk unit weight is 16 kilonewton per meter cube, and this is not saturated like this soil and this soil, and the height of fill is say 3 meter. Now we want to calculate the stresses at this point A again after the fill has been placed. So the total stress at point A after the fill has been placed will be 2 times 18, that was before already, but there will be an additional stress, that is 3 times 16 due to this fill placement. And the total stress is 84 kilonewton per meter square. And the pore water stress still remains the same like before, 20, and the effective stress now is 64. So there is an increase in effective stress at point A, and this increase has been caused by the change in the total stress, not in the pore water stress. If you see, the total stress was 36, now it is 84. The pore water stress was 20, and even now it is 20. So the change here is caused by the total stress. So this example shows how there may be a change or increase in the effective stress due to increase in total stress and not due to change in pore pressure. Let us take another example, and this time instead of applying a large infinite size of load like a fill placement, we'll now use a finite size of loading on the same soil layers. The clay layer, the saturated unit weight is 18 kilonewton per meter cube, underlain by a sand layer, and these two layers are fully submerged, so they are fully saturated. So the total stress at in this scenario, in the zero scenario, is 36. Pore water stress is 20, and the effective stress is 16. Now, if we place a column footing of 4 meter by 4 meter dimension carrying a load equal to 2000 kilonewton, there will be change in total stress, and we'll see if there is any change. There will not be any change in the pore water stress, and there will be change in the effective stress. So how to calculate this total stress applied by this 2000 kilonewton column load through this 4 meter by 4 meter base? So there will be a stress distribution underneath the footing or the base at a rate of 2 vertical is to 1 horizontal. So if you go to 2 meter down, there will be a horizontal shift in the spread of 1 meter. So 1 meter on this side and 1 meter on that side. So the length or the dimension of this contact or the fictitious footing will be 6 meter in each side. So this will be a 6 meter by 6 meter footing, okay, a fictitious one. So this was 4 meter by 4 meter. After spread, this will become 6 meter by 6 meter. So this has been showed here. So the stress at this point will be 2 times 18, that was already there, and due to the column load we'll have P divided by A, that is 2000 is the load, divided by area will be 4 plus 2 times 4 plus 2, and that should give you a total stress equal to 92 kilonewton per meter square. And the pole water stress will remain as before, that is 20, and the effective stress will be now 72 kilonewton per meter square. So this also demonstrates that the effective stress has changed due to the change in the total stress and not due to the change in pore pressure. Okay. Now let us pick up another example. The change in effective stress due to lowering of groundwater table. In this case, the groundwater table was at the surface. That is what we have been considering so far. But now we'll consider that what happens in the stresses if the water table comes down. Okay, so let us consider this initial scenario first. The total stress is 54 like before, the pore water stress is 30, and the effective stress is 24. Now if the water table is lowered by 1 meter, okay, then what are the changes in the stresses at point A? Let us see that. So the total stress will be 3 times 18. I have made a small assumption here. When there will be a lowering of groundwater table, of course you can understand that the soil will not remain fully saturated. Okay, so the density should be different from 18. But since this is only 1 meter, and due to capillary rise or the suction through the micropores in the soils, this will, for all practical purpose, may be considered saturated, and that is the assumption I have made just to keep it simple. Okay, and the total stress I have calculated again as 3 times 18. Didn't make the density difference for this 1 meter and this 2 meter. Okay, and the pore water stress, now there will be some change here. Okay, what will be the change? Now the pore water stress will be due to this height of water column. That is, earlier it was 3 meter below the surface, now it is 2 meter below the water table. Earlier it was 3 meter below the water table. So the 3 minus 1, that is the change, and the height of water column above point A is now 2 meter. So that should give you a pore water stress of 20 kilonewton per meter square, and there is the change. Okay, so the effective stress now will increase. Let's see. So 54 minus 20 will give you 34. Earlier it was 24. So this increase in effective stress has been caused by lowering of the water table, and this increase is actually the difference of the pore water pressure or the pore water stresses. Okay, earlier it was 30 and now it is 20. So the amount of pore water stress that has been reduced is transferred now to the solid particles, and that is the beauty of that is the concept of effective stress. The total stress will be shared between the pore water and the soil skeletons. So the amount of pore water that has not been taken by the water in the void spaces will now be transferred to the solid particles, and that is why there is an increase of 10 kilonewton per meter square in the effective stress at point A, right? And that is exactly what we have written here. The increase is equal to the change in pore water pressure, and that is equal to 30 minus 20 is equal to 10 kilonewton per meter square. So this is an example where to demonstrate that effective stress may increase as well due to the change in pore water pressure. It is not always due to the external applied load or stress. It may also be caused by the change in pore pressure. So the concluding remarks are: number one, the effective stress in a submerged soil mass does not change due to height of water column above it. I have demonstrated with 2, 3, 4, 5, 6 examples. Okay, and the effective stress changes due to wide area field placement, that is due to the change in the total stress, and also changes due to loading through finite size area, that is an example of the footing, column footing, and the change in the effective stress is caused by the change in the total stress, and also by lowering of groundwater table, which causes the reduction in pore water stress and increase in effective stress. And all these concepts of effective stress, in fact, these understandings comprise the backbone of shear strength and compressibility behavior of soil that is to follow in my next lectures. Okay. Thanks very much. Thanks for watching this. I hope I'll come back soon with the understanding of compressibility behavior of soil in my next lecture. Thanks very much.